Hello, and welcome to another wonderful episode of the New York City Category Theory Seminar. This is the final episode of the season finale for the spring 2022, and we have Gershom Bazerman speaking about traversals of infinite structures. Take it away, Gershom.
Okay, so I'm Gershom Bazerman. I work at Arista. I was born in the New York area. I studied computer science at Berkeley. I'm back in the New York area. I think that covers the usual. And I'm going to tell you about a computer science problem, trying to make it sound as categorical as possible, which is not too hard. There's a lot of category theory in there, but to make it of interest here. Solution, and then this is sort of a work in progress in terms of writing it up and maybe formalizing a couple bits that haven't been formalized. And so it's applied category theory in computer science in a way that might interest people who are curious how category theory gets applied in computer science.
And that's the coolest background ever, because that's our room that we have the in-person seminars.
Yeah, that's I put in the background of the room that I wish I was presenting this in as a chalk talk instead of struggling with Beamer slides and the usual woes therein. Nosen asked me to make sure that I would define everything carefully as I was presenting, and don't worry, I will, because if I didn't, I wouldn't have a talk, right? Most of the talk is going to be setting it up. The result sort of just follows from once you know what's going on here. So it's not that great a result, but all the setup, and then you put it together and you get it. Some very quick review, and it's a category theory seminar. I'm not going to tell you what a category is in any depth, and I'm going to hope you remember what a monoidal category is and a monoidal endofunctor are. But in case you don't, a monoidal category is a category that has a functor that sort of gives a monoid operation on its objects, and a monoidal endofunctor, or a lax one, is one where that commutes laxly with the monoidal operations of the source and target categories of the functor. Now, this is something, that's normal category theory. Now, here's something that comes all the way from computer science, but it was given by Jaskliov and Ripet in a category theory formulation, which I'm going to tell you. Because there's an interesting result in its own. So when you have two monads, people have often studied the distributive laws of monads, right? Which would be a natural transformation Mn to Nm, sort of distributing one monad over the other. And then when you have two monads in distributive laws, you can get sort of a compound monad out of the two of them put together, which is one of the reasons that's of interest. This is sort of inspired by that. This is another notion of a different sort of distributive law you can have. And what makes this one interesting is it's a universal distributive law. So given any functor f and any other functor g, you can always ask when can you sort of swap f and g by some sort of natural transformation, and then you could also maybe put some coherence conditions on that. So for any arbitrary functor f, consider only monoidal functors m. And you can have a distributive law sort of that's, sends f composed with m to m composed with f. And in fact, if you have a functor such that for every monoidal functor m, you have such a distributive law. And furthermore, that the distributive law on the identity functor works as one would hope. Distributive law composes in this way right here, right? So if you sort of apply the distribution and then you sort of, you're halfway done, and then you apply the distribution inside the result, you get the full distribution as opposed to distributing over the composition. And that has a naturality, which makes it a family. So that when you have natural transformations between, which are natural monoidal transformations between monoidal functors. Distribution commutes with them naturally. That's what makes it sort of a natural family of such distributive laws. And this maybe feels like a bit of an odd concept, but it's actually a very fancy way of saying a very common thing in computer science, which we'll get to, which is the reason it's called a traversal. And this is the categorical formulation of it. But let's just stick to category theory. Let's give some examples of what sorts of functors are equipped with such natural transformations, just sticking to set. So endofunctors on set. Well, any representable endofunctor, you can sort of do a pointwise distribution that, sort of sums over or products over all the possible elements of the codomain and applies the functor pointwise. And then it sort of, monoidally, it uses the monoidal action to sort of mush together all the results. Sums, again, you can have pointwise action on the components. And okay, so what other sorts of functors that aren't generated by representables and sums can you have where you get such a family of distributive laws? And that's it, or at least in set. This is a theorem in set only that by independently, there's two theorems, one by a very large team, including Gibbons and the late Richard Byrd and many other names. And also R. O'Connor and Jaskuloff had their own independent version of this. They both, they're the same in the high level, but they're different in the details. They show that, and they have slightly different settings, but basically set. A functor will admit a traversal if and only if it's a sum of finitary representables, which is also known as a finitary polynomial functor, because if you have sums of these representables, which you can write as powers, then it's going to look exactly like a polynomial in one variable. And so polynomial functors are of a lot of interest lately. The Topos Institute has now run 2 sort of week-long seminars on them, and there's actually a book by Spivak that runs through a lot of her work. And in their more general formulation, they also intersect with like universes for type theories. They intersect with some questions and so some characterizations of operads and all of that. But this characterization of finitary polynomial and endofunctors in set is very little known in this community. So it's a very there's a number of other characterizations, but this one is very particular in computer science-y. But I think it's neat that you can add it to the zoo of many different ways to describe polynomial endofunctors.
Gershom, could you tell us the usual way of defining polynomial functors?
Well, the way I sketched it is the way that it's a sum of representables.
That's it.
But in set, if you want to move to a broader setup, I would have to draw you a picture. You've got you can generalize it much more to a much bigger category or class of categories, and that need to be able to admit some notion of a sigma and product, and then you sort of move to the sigma and product within that category. Right. So you need like enough limits and stuff lying around. And then you get sort of a diagram of 3 functors that represent the sigma and product. But even for the polynomial endofunctor, sum of representables instead is how they would tend to think of it. The difference here is that the characterization is that being a polynomial endofunctor is equivalent to having a family of traversals, or having a traversal, which is a family of distributive laws. And that characterization is what's very unknown.
Okay.
So, does that make sense?
Yeah. Is there an intuition of why it's so popular? In other words, what things what phenomenon is it mimicking that makes it so popular?
Gosh, there's too many intuitions for me to give here in a way. I will say that the reason it is interesting in programming languages is due to the fact that they correspond to what Ghani et al. Called containers, which were also known as shapely data types earlier, which is sort of their indexed data, the data types that are sort of indexed and have an arity at each point. And that's all strictly positive data types fall into that construction in most setups. So that's in computer science why they come up. Why they come up elsewhere, there's almost too many reasons. You'll have to watch one of Steve X's talks or read the book to see all the uses. People like them because they can represent sort of branching graphs. And then, as I said, there's a characterization theorem that relates monads on them to operads. And there's some sort of characterization theorem that relates comonoids on them to categories somehow. But I couldn't tell you how that works.
Well, also another thing, just to mention, with what Gershom said, that's from the computer side, but that's pretty close to pure math with what you would do with universal algebra.
Right. Fair enough. So anyway, they're pretty ubiquitous. And you get this neat characterization theorem that these traversables, things that admit a traversal, correspond to them. And here's my sketch of how both those proofs work. And like I said, this is what I was trying to delete and couldn't. I don't believe there should be a pi here because that's redundant with the power. You don't need both. If you got a functor, and you want to give it and it admits a traversal, then you can consider that functor at unit and or star at 1, and sort of index by that and sum over that the arity, and you can get the arity of each point that you're indexing at because everything's in set. Otherwise, this is meaningless. And then you can sum over that and you get, and then ignore the pi again, and then you get that's precisely your sum of representables. And well, you've got this and you've got that. Now you need to prove this is an ISO, and that's where the trickiness comes in, where you use a couple of monoidal functors built-in set that can sort of walk through an element of this gadget, and using your family of traversals, they can, quote, traverse out all the, quote, A inside of it into a collection. And then going the other way, you can, again, sort of monoidally traverse through and put back all the A you took out. So you can map between FA and F star across the number of A's you've taken out. And that's an extremely computer sciencey proof because it's super operational and it involves sort of foreign to mathematical concepts. Like thinking of this as an actual structure you're walking through and taking things out of and putting them back into. But it turns out that the monoidal structure sort of on that is that on the, that you're requiring to commute with the distribution is exactly what you need to do that, because it's a way of actually ordering the elements here. So in fact, you have precisely as many possible traversals as you have sort of permutations of the arities. So this stuff actually relates to combinatorial species as well, I should note. And containers are basically permutation-free combinatorial species, which is another reason that one might notice that they arise fairly frequently. But I don't have time to go into that. So anyway, that's the very high-level sketch of the proof. But it basically, once you see the two shapes, you just have to then construct a very clever monoid in both that you can traverse with to get both sides of the isomorphism, and then show that it's actually an iso. So now I'm going to give you some examples of how these monoidal endofunctors arise in Haskell. What are your building blocks for building this clever stuff? Well, before I just said monoidal endofunctors, I'm sort of cheating here because I'm just going to note that, well, actually they're all closed monoidal because your functors in Haskell, or really any Cartesian closed category, which we're pretending Haskell is it's not, are strong. And once you admit a strength, that means that you have this closed operation as well, which I won't go into. But it is helpful to know that. I should have fixed another typo. So here's reader, which is sort of the Hom functor, Hom C A, and but we call it reader because it represents being an environment where you can read out your environment variable, the Hom C. Writer, which is you tensor with M being a monoid, and that looks familiar in like a topos theoretic sense, but I won't go into that. And there's maybe, which is A goes to 1 plus A, so you have optionality. You can either have the thing or you can fail. And these guys are all monads, but they're also all closed monoidal endofunctors. And in fact, if you're in a Cartesian closed category, I believe that this holds in all Cartesian closed categories, then every monad in a Cartesian closed category also gives rise to a monoid, or a monoidal endofunctor rather, which is not always the case, right? The sort of join of a monad is not related to being a monoidal functor in a typical category, but in a Cartesian closed category, you get strength, and therefore it somehow is. The enriched category theorist in the Australian school could explain this. It's not that difficult, but I can't explain it all right now. However, you also do have more monoidal endofunctors in Haskell or than you have monads, right? It's not a correspondence, it's a one-way thing. So for example, the functor that sends everything to a single monoid object is not going to be a monad, but it is going to be a closed monoidal endofunctor. And this is my fancy way of just running a list, but if you have pointwise product as the monoidal action, that's not a monad. It is if you have concatenation as the monoidal action. So these gadgets are
they don't have units or multiplications, or they don't have one of them, or they don't have both of them.
Const doesn't have a unit, I believe, and zip list doesn't have a multiplication, I think. So those are the two typically canonical examples of the different ways they fail.
They all have units.
Sorry, I misspoke. Well, there's something. Const doesn't have something. Yeah, right. It doesn't obey the right laws with unit or something. So.
Can you say a little bit about what reader and writer do, like in Haskell, like what they're used for?
Well, reader corresponds to a computation existing in an environment, right? So, like, this is instead of just having A's, you have A's that are all fibered over, or indexed by C, right? And so, suppose C is a configuration, right? So, suppose you've got some pure program A, right? Some value, some program that computes a value. But all the computation happens in a setting where you can, quote, read, the command line parameters passed to the program is like a list of strings. That would be your C. So that's used for passing around an environment, and it can actually be used to represent sort of your variable scope environment if you're writing an evaluator for the lambda calculus or the like. And writer is, well, M is usually some sort of log. So, you've got a bunch of computations that produce stuff, and you're doing your normal computations, but along the way, you're just tracking some monoid on the side, and that monoid might be a list of strings about log messages, like side channel information you're tossing out along the way. Is that helpful?
Yeah, gotcha, thanks.
And then maybe represents failure. So, you divide, two numbers, and, well, you either get the result or you get error divided by 0. So, okay. So that's closed monoidal endofunctors, and why we care about them is they represent a wide class of effects, and wider than monads, in fact. So now, so what is this traversable thing I told you that, this family of distributive laws, what does that look like in Haskell is, well, you take something like one of these effects, and now we're going to consider really just lists, say, as a canonical traversable functor. That's a good example of stuff. So we can take a whole list of functions that each require some context, and then each give back a string. and get back a single function that you pass the context into and gives you back all the strings at once, right? So that's very natural, right? As a notion of a traversal. That's what happens when you commute, the HOM in the list functors. And, or here we take a list of actions producing ints, say, and then writing this log as a side effect. And now you get a single action that gives you all the ints and then writes out, all the joint logs together. And then state, which I didn't tell you about, you can do that. So sequence interactions with some sort of store that, everyone has access to and then can sequentially also mutate. Or, take a list of possibly failing actions to a single action that either gives you all the results, or if any of them failed, says, whoops, something failed. And these are all examples of traversals. So given list, this is if you traverse list or sequence list with various monoidal choices of monoidal functors. So in a sense, it's the essence of sequencing actions, right? And that's why, and so therefore, so the point being, traversals are ubiquitous. And in fact, I believe one of the papers of Gibbons was actually named the essence of the iterator pattern. So that's the line of argument here, is that this categorical gadget I told you is actually all over the place. And so now we introduce the problem I'm looking at. Is I told you this just fantastic theorem that we can characterize traversable functors precisely as finitary containers, or finitary polynomial functors. However, if we're in a language like Haskell, we don't only have finitary structures, we have potentially infinite structures, because we have a fixed point operator, and we're a non-strict language. So I can construct streams of numbers that go on forever. And I can traverse them and get results and actually do work sometimes. But this doesn't correspond to the correspondence theorem. And so there's sort of a mismatch that's very confusing and irritating, right? You have this wonderful characterization theorem, and then it turns out in practice, people are doing things where they're traversing infinite streams productively, which is, to say that they're actually, at every step of the resultant stream, you can still look at it, and it's non-bottom. You've actually gotten an answer out, so it's no less defined than the stream you put in. Yet somehow, and so this is what I want to explain. That's sort of the point of the work, and really, the reason for the mismatch is the correspondence proof takes place in set, and well, Haskell doesn't take semantics in set. We like to pretend it does, but only the total fragment of the language takes semantics in set, and the total fragment of the language is precisely, which is the one without infinite recursion. And the total fragment of the language, once you restrict yourself to that, then of course, finitary polynomial functors is the right thing to get out. But we're in a language that's bigger than the total fragment. So we need a model of the language that we can reason about this stuff in. And it's not the set-based model in which that other correspondence proof took place. So really the insight of this work really just begins with noticing that there's another good model one can look at, which is called guarded recursion, and it's relatively modern. And so I'm gonna tell you about it. Except I'm not going to tell you about it immediately. I'm going to tell you about something else first, provability logic, which Sergey Adamov is not here, but I mentioned this to him because that he might want to come, because I thought it's interesting how far back this idea goes, even though it's really very recent that it's come its way into computer science, and even more recent people have started to make real use of it. But I thought this crowd would appreciate it. So we start with, Gödel, who else? And it was not initially a system designed to aid in the incompleteness proofs. It was later used for that. But it's a way of validating the Brouwer thesis that intuitionistic proofs is equivalent to provability. So he had to come up with an internal logic or an intuitionistic system that had an internal notion of provability. And so my joke is that this is the original proof carrying code. So he had an intuitionistic logic that had provability predicates. And then a very different thing, but sort of inspired by that, came about in pieces, but beginning with Loeb, who did not originally present this modally as a modal logic in itself. That came a bit later, involving a lot of people actually around CUNY, which I won't get into. But initially, I'm writing it modally just to skip steps. He showed that in PA, you have this general theorem that if box here means provable, so if provable A implies A is provable, then that's equivalent to A already being provable. And so that's how you state that internally in provability logic, or Gödel-Loeb provability logic, known as GL, is provable A imply, if it's provable that provable A implies A, then it's provable that A. And GL logic is super cool, and I can't go into all the things people have done with it, but it gives you a nice way to actually do Gödel's second theorem and many other things. The models of it are very neat. But now we're going to fast forward 50 years, and we hit Nakano in 2000, who actually worked under, I guess, suggestions from Pfefferman on this, produced a modal logic for self-referential formulae. And Nakano had a particular way of studying the proof system programs paradigm that with logic they called PX. They wanted to extend this to cover a broader class of programs, including programs with sort of more sorts of recursion than could be handled in ad hoc ways before. And so you needed a way to have self-reference in a program, and you needed, and here I say, as stratified by a hereditary accessibility relation, which is, just a way to say that you need sort of a notion of successive universes, just like type theory initially did, so that your self-reference always put you in a bigger universe. So you weren't really referring to the same self, so to speak, but the self at the next stage. And so then this all gets internalized in modality. And the fixed point operator looks shockingly similar. There's no reference in the first paper actually to Loeb, but the fixed points operator is like Loeb if you take off one layer of boxes. And indeed, the next year, Nakano published a second paper and showed that Nakano's modal logic for self-referential formulae or recursion is a conservative extension to Loeb logic. And later, McBride and Atke noticed, and I just say noticed because it's not that in fact, that since the modality is the K modality, then it has the structure of a closed monoidal endofunctor, and so you can internalize it into a lot of, and you can think of sort of the delay operator, as Nakano ended up calling it, as an effect. And you can build a system like that, which McBride, Atke, and many others have done since. And then these systems are called guarded recursion. Because here, the normal fixed point operator, you just don't have this box, right? And you just take the fixed point of A to A. But here, we guard our recursion by the box, right? And the box is pronounced, quote, later. So, and point is that you always have a function A to later A, right? Like I said, it's like logic K plus this operator. And you're always functorial under the box. So, if you have A to B, then you have box A to box B. And furthermore, you have, if you have box A to B, then you have box A to box B as well. But what you do not have is, right, in general, is box A to A. So only for very special A do you have something like this. And that's what makes the machine go. Is you need a way to take some success now, because it's under a later, and say, well, yeah, but I can put it somewhere without looking at it. And that's actually corresponds precisely to the discipline you have to put yourself under when you take fixed points just that aren't guarded, if you want to make sure that they actually don't just yield non-termination. All right, so now we go to semantic models and back to category theory land. So GL logic takes semantics and crypty models and is complete with respect to transitive, conversely well-founded frames, which is frames with no infinite ascending sequences. Now, very recently, in our terms, right, 10 years ago, Lars Birkedal, Rasmus Mogelberg, and a few collaborators published First Steps in Synthetic Guarded Domain Theory, where they gave us categorical models for guarded recursion in something called the topos of trees, which I'm going to tell you about. And the neat thing, I think, is that you can really think of the topos of trees as a categorification of these cryptic models with respect to frames with no infinite ascending sequences. I'm not going to prove that. I'm just telling you, you can probably think about it that way. And that's a nice correspondence. And they actually did some pretty neat stuff, is they actually built inside the internal logic of this topos of trees, they built a step indexed, as they call, model of a programming language with general recursion. And there's been a lot of wonderful work from them and others since, which I can't summarize on guarded recursion. But I am going to tell you about the topos of trees because it's a category 30 seminar. So I'm going to tell you about a category. So you have the ordered category generated by the first uncountable ordinal, right? So, just, 1 to 2 to, 1 is less than 2 is less than 3 is less than 4, right? And on up, but you got a point at infinity. And now you just take tree sheaves on it. And so what happens? Well, objects are now going to be sequences indexed by, 1, 2, 3, 4, 5, so forth. And because it's, it's contravariant, I should have given an op in there. I'm sorry. But because it's, a contravariant functor, it's tree sheaves, then your restriction maps are going to go the other way. And James helped me figure this out because I knew this and I confused myself, and then he helped me know it better. Right. So for each sort of sequence of objects, you're going to say for each point or in the set at this stage, like here's the set at stage 0, the set at stage 1, the set at stage 2, every element in there, right? Because you have a map coming back, not every every element in there has to come from something at stage 1. And so that tells you where the elements in here evolved from with regards to here. So a stream of natural numbers is going to be, well, at stage 1, you have 1 natural number. At stage 2, you have 2. At stage 3, you have 3, right? Because you have the first one, then you have also the next one, and then you have, the first 2 and also the next one. And then your projection maps backwards will tell you, okay, that this, if you've got 2 here, well, one of them came from there and the other is sort of introduced only at that stage. So that sends your object maps backwards. That's like, I think I just confused you because of how I said it again.
One question. Is there a condition on the A omega?
No, not that I know of.
Wait, so is there a point A omega here?
Not really. I should have just had ... right? Because this is, yeah, I mean, there is a quote point at infinity, right? But you'll never get there. It just might stabilize, right? So anyway, there's no restriction on it. Maybe I shouldn't have even written it if it confuses you. But so the intuition is the future is fibered over the past, right? Which is to say that, for every, you have a map, backwards.
Come to think of it, actually, if you shouldn't have written it, because for that, if you had omega plus 1 to set, then you'd have an A omega. But if you had just omega to set, you don't have, right? Because omega is just all the finite ones. Omega plus 1.
Yeah, that might have been better. But hopefully this part makes sense in a way that, you have the set of pairs of naturals, and then the projection function, which is called the restriction map, restricts to only the stuff you knew at the prior stage. And so that's what objects in the topos of trees look like. And arguably it really should be called the topos of forests, because it branches, but you don't always necessarily start with, sort of a root. You might start with a whole bunch of roots. And here's a couple other, so here is what the truth object in the topos of trees looks like. It's actually, it's, 1 point set, the 2 point set, the 3 point set, the 4 point set, and restriction maps sort of truncate. So if I'm at 2, the number 2 out of 4, and then I restrict back, then that's fine. If I'm at 4 and then I restrict back, I have to get down to 3. And it tells you how long something remains true, so to speak, intuitively. And now you get your version of the later modality here, which is you got a closed monoidal endofunctor that sends any sequence like this to a sequence that's shifted up by 1 and just has a point, right? So it says, well, first you just have 1 point, and then you have everything that you had. So it sort of delays everything by 1 point. And so that internalizes the later modality, and their paper also showed that you actually get this internalized on types and terms both. So that's very nice. You get it as a term operator and you get it as an operator on objects. And I just thought I'd note this because it's an interesting connection to other elements of topos theory that typically restriction maps will be surjections, and the only times they're not are when something sort of becomes false at some point. And the objects where restriction maps are surjections, they call total, but this corresponds to being a flask or a flabby sheaf in other places where people look at sheaves. And I just think that's neat that this notion of a flask or flabby sheaf comes up, and they make use of it in some of their proofs in this paper. Okay, so that's all I'm really going to tell you about the topos of trees, except there's much fancier things than it that people look at these days for modeling clock stuff, which I'm not going to tell you about. So now we've got the setting, and we're really not going to work in the topos of trees. We're going to just work in this logic that takes semantics there, right? Which is a logic that's like Nakano's, has this modal operator later. Well, so what's the difference? Now I'm not just going to want to traverse a list. I'm going to want to traverse a stream, and a stream is something where at each recursion, there's an additional sort of, later guarding it. So we know by prior work that in general, traversable functors are closed under, sums and representables, and also therefore under products. But here, we're also going to have these laters in the way of stuff. So we also need to be closed under later. Right, which is to say that if FM is traversable and we want to be closed under later, then later F should also be, or if F is traversable, then we want later F to be traversable. So how do we do that? Well, we need a map precisely that sort of swaps not just the M with the F, but the M with the later F. Right. So, but if we examine this a bit, we decompose it and we say, well, the first thing we can do is we can, take the action of later on the distribution we already have, or the traversal we already have, and that's going to send, that's going to give you now later FM to later MF. All right, and now all that's left to do is commute the later and the M. So we find out that the condition for traversability on a guarded recursive functor isn't adding more conditions to the guarded recursive functor itself. It's adding conditions to the monoidal functors. So we can't just traverse it with any old monoidal functor. We have to traverse it with a monoidal functor that admits this distributive law, that commutes with later. And once you do that, then you get the result that it's necessary and sufficient to commute with functors closed under some product, blah, 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 and later, which are, in fact, the guarded recursive functors sort of given rise to naturally from your standard polynomial functors, if you want to give them guarded recursive semantics, is the best way I could maybe say that. I'm not quite sure how else to pick it out. I don't know how to characterize it directly in the topos of trees, but I can tell you they're the ones of interest if you're using the topos of trees to model the stuff that you're encountering in sort of standard, sort of normal quote unquote terms in your functional language. So what are some examples of these guarded recursive functors? Rather of these functors that commute with later? Well, Hom, again, always works, where C is a constant. Sum never works. So A plus 1, you cannot commute with later. Product by a constant works, but only for very special constants. And I worked this out and it made me kind of mad because I wish it didn't work. But you actually can have exponentiation by something involving the A that you're functorial in, with, if this is just a contravariant functor F. And again, the same sort of very special C. And the idea is, right, because these sums are disallowed, you can always predict the outermost constructor, if you're thinking programming language wise, but the outermost shape of the thing. And so Jane Saussure actually suggested the name predictable functor for these, which I think is a great name. And right, so the notion is if I had A plus 1, right, how would I commute, just to show how this doesn't work? If I have later of A plus 1, then what we would want is to turn that into later of A plus 1. But that would require that I could somehow look inside the later to decide if it was, this or that side of the sum. And I can't do that sort of definitionally. That's the whole point of that later, is that it guards that. So so we can also, so here you have an option, you have a choice. That's what a sum is. And because we're choice free and all these other things, we can, quote, predict it. And now I'm going to tell you what this very special C is, which is irritating. It's one we're calling stable. So, I probably pointed out above, most things don't have a map later A to A or later C to C. Of those that do, even fewer have a map where that's actually an equivalence up to, again, I haven't told you what sort of equivalence. And, but if you do have that, what are some examples? Well, false has that, unit has that, few more interesting things have that as well. Then you're what I'm going to call stable, which is to say that you can really sort of ignore the fact that these laters pile up, because you can just take this equivalence map. And here is my sketch of the delay, or the Capretta style delay, which is a partiality monad as a functor. So either I have an A or I have to wait for the A. And then at step 2, well, either I had an A before, or now I have an A, or I have to keep waiting. And at step 3, well, I have an A now, or I had an A to begin with. It took me 1 step to get an A. It took me 2 steps to get an A, or I have to keep waiting. And this corresponds to what's called the Capretta monad for encoding partiality. And you can write this inside of a guarded recursive system. And it's a stable type, and in a sense, it's the universal stabilization of any type. It's not the most useful stable variant of a type, but it's always there. So hopefully that makes a little sense. Is if you drew this as a real tree, you'd have a line at the bottom for 1, and then it would come up at step 1, so it could branch to 1 or A, and then at step 2, that would be the same, but it would come up again, and you could branch to, so it would be, you'd get more and more sort of horizontal lines stacking on top of each other as you went forward in time. And so in here, the special C that you can product by or take this terrible exponent to is are stable. And now I told you up to some notion of similarity, and I'm going to tell you the notion of similarity we introduced for this purpose. And we reached to a notion called bisimulation, which was used in studying concurrent programs, but it's useful for this sort of stuff too. And people have studied Capretta-style monads posted by bisimulation before. I don't know if they've really used them in guarded recursion, and I've got sort of a twist on it. So a classic bisimulation is a relation on 2 streams given by a sequence of pairs, right? So each of these streams is indexed by time, and then you've got these pairs and they're each non-decreasing as you move forward in each component. And so it just sort of says, well, you move this guy up a bit, and then you move this guy up a bit, then you move this guy up more, then you move this one up. And you can only go forward. And as long as you keep doing this, the two streams are always going to be sort of have the same values on both sides. And you're, of course, going to have to step one step at a time. So it's a way, if you have the same events happening in the quote same order, but sort of their relative clocks may be different. It's a way of resyncing up those relative clocks. And that's how one tends to look at if processes are equivalent in a concurrent setting. And it's also good for what we're looking at. Now, the thing is, we want to sort of cheat a bit because it's sort of a pain to work with these things. And well, we're really working with terms that are supposed to model terms that live in a more standard notion of what would be called a domain, which is, a setting for the semantics of possibly non-terminating programs. And this is sort of, a refinement of domains is the synthetic guarded domain theory. So, well, why don't we just project these gadgets we have now that are much richer than standard domains and just project them into normal domains and then say, are they equal as objects in, this category of domains we pick? So we're just going to evaluate them, so to speak. And see if an evaluator, and you say two objects are bisimilar, take the same semantics under some arbitrary notion of evaluation that we pick. And then we're not quite done yet because that tells us when two objects are bisimilar as a relation. But what we really want to do is consider morphisms that are not necessarily invertible, right? That send something to something else that is bisimilar to it. And we call those gadgets guarded weak biequivalences. And they're morphisms A to B that send terms to bisimilar terms. And they're sort of neat because they're directed, but they're weakly similar. So you can show they satisfy 2 out of 3, and I think 2 out of 6, which is sort of a way of saying that you get a bit of a homotopical category out of this. And I don't know what you do with it, but it feels like a very natural way to structure things here. I should say to make it work, it doesn't send term. Yeah, that to make it work, we note that the bisimilarity here, we're not asking actually that these two, that they evaluate to the same object. We ask that they evaluate to equivalent objects by the notion of equivalence given, of ISO in the evaluation domain. And that's what I think makes this work, although it's a bit weird from a programming standpoint. The not on the noseness helps with these properties. Okay, you put it all together and you get the result, which is that if you have a potentially infinite traversable functor in Haskell, right? Like actually the actual list functor in Haskell, where you can lists also include infinite streams. You can infinitely traverse it precisely when you go by a monoidal functor, which is predictable in the sense given above. I think that's a pretty nice result because that's basically a full answer almost. There's a lot of complications to what the question that was posed is we have a setting in which we can understand this thing that didn't make sense before, and we have a pretty good characterization theorem. I should note, by the way, I do not claim this is an exhaustive enumeration. I can't think of any other things that might be predictable, but I make no claim that this is all predictable things. So that's a bit of a missing piece to it. You have a characterization theorem, but it would be nice to get an enumeration. That I think covers most of my slides. I hit a slide called rampant speculation. I was trying to edit that to make some of the speculation more and less rampant, and then I ran out of time there. But let me see if maybe I've got something a bit more in my notes to. Oh yeah, this is what I wanted to talk about that didn't make it to those slides. I want to tell you the actual setting that this is all done in. So in the work I'm doing, we've actually constructed this guarded recursive world within Haskell as an internal guarded recursive modality with terms constructed using guarded recursion and making use of later. So we can use internal equational reasoning. And we have an evaluation function that has terms as fibered. The guarded terms are somehow fibered over normal terms because they're different sort of ways of refine, limit it to only having delays in certain places. And because evaluation is defined via it's productively, except when you hit an arrow type on the left-hand side, you've got to sort of project back into the evaluated domain or into the source domain from the evaluated evaluation domain. You end up with something that looks a lot like a poor man's cobbled together logical relations. And in fact, because this is done with type classes, what you end up with is each term is sort of paired with its evaluation implicitly. And if you think of that categorically, that's sort of like a common construction, and you get sort of like, and that's sort of a tape relation is what they would tend to call such a thing. This is all now, like I said, this is stuff I haven't fully worked out. It's just how it feels categorically what's going on. And you have similar things that are definitely shown to be comonads, in clock type theory, where you can sort of extract finite information out from under a later in certain cases. And there's a general thing that looks like, really looks like a comonad that sort of into the full universe of general terms. And delay sort of looks like an internal monad on the other side, where you can sort of evaluate something from out of guarded terms, and then you can delay it back in to this semi-evaluated universe. And that also is, and so it feels like there might be people are sorting around there, but I don't know, but that would be interesting. And another open question is, I pointed out you have this 2 out of 6 thing or whatever. So is there some notion of a localization of the topos of trees by classic bisimulation? It's not going to give it topos, I'm almost certain, but would that be interesting? And also, if you sort of glue by the pairing of terms in their evaluations, then you might also get something sort of interesting. And that is not the way people have been relating these guarded models to other models in the past. It's just another thing one could try that sort of occurred to me while I was thinking about this work. And is there anything else I'd know? Oh yeah, some fiddly bits that are more applied is, to state these theorems right, you need to have a precise definition of what it means to be productive, which is usually not, to my done satisfactorily. I think in the sense that you don't want to be universally productive. You got to be, productiveness is usually defined just on streams or something, as for any finite observation on the stream, you get an answer in finite time. But you sort of need productiveness over arbitrary structures, and you also need a notion of productiveness that applies to portions of structures, because some of these traversals are going to yield something that's a quote productive stream, but then that's going to be paired with like a state that's inaccessible. Like, you're never going to get the final log, even though maybe you can read pieces of the log. So there's also a bit of cleverness when you model different duplicative functors in Haskell in this guarded recursive realm. You've got to pick terms are fibered over them. You got to pick the right guarded term that captures the semantics you want, which is sort of precise enough to all the ways in which you can observe it. And that's pretty interesting. That in some ways it gives you this one answer, but it also opens up a bunch of ways of analyzing programs much more granularly in terms of where they terminate and where they don't, within portions of data structures than the basic tools give you. I think people do this a lot in their heads, but they don't necessarily have a formal language for it. Maybe this is not quite formal enough, but I think it's not a bad start. All right. I'm about done. So thanks for your time, everyone. And I hope you found it interesting.
Oh, thank you. Thank you very much. It's a whole world. Anyways, let's thank our speaker. Any questions? Ray?
Is the functor of pairs a predictable functor that's not classified there?
What do you mean the functor of pairs?
So just like A cross A.
No, that's the same as exponentiation, right? Because that's two arrow A.
But is 2 like the type 2? Isn't that not? Is that stable?
No, but
Because you
A
can't
to the
get
C.
funds out.
It's A to the C is always fine for any C. It's C to the
Any C
A
whatsoever.
that's fine. Yeah, A to the C is always fine. It's C to the A that you have to watch out for.
And C like times
And
A
C
as well.
times A you have to watch out for. But representable functors are in fact then the nicest class of predictable functors.
Okay,
Representable following the trend of being the nicest class of about every sort of functor.
If I could ask one more, do you have any other I guess interesting or sort of useful examples of these predictable functors besides the, I guess, reader and writing logs?
Well, I mean, I didn't go into state because there's a bit of trickiness. That, like I said, that's one of the clever ones. Is the typical, and state is very general. The typical state is not going to look like it can be made predictable because it's got stuff in the contravariant and covariant position and stuff. However, there's a lovely decomposition of state by Tarmo, Ustalu, and collaborators into what he calls update monad, which sort of pairs a reader on a state with a writer on a monoidal action on the state. And once you take that decomposition, I can't get to you right now, but then you can actually model the state monad in a very rich, really nice way with this. That in some ways it's a bit nicer than the standard state monad because it actually gives you a trace of all the different states that occurred at any point in the program, in the result, rather than just the final state. So those are, I mean, most of your canonical examples of functors look something like that. The ones that don't look something like the continuation monad, that's the one that I showed is modeled when the result of the continuation is delayable or is stable. However, I would say it's spectacularly, so far I found it spectacularly useless because the actual stable thing it gives you is infinitely delayed. So that's why it makes me mad is the formula works, but I think it right. So again, just the fact the formula works doesn't mean it's useful. The formula works, but the result it yields is about the most useful thing you could ask for. So you almost might as well not work. Really figure out how to present that well. But
got it. Thanks.
Any other questions?
I don't know if you said this, but these are traversals in the sense of like optics.
I mean, the optics get their notion of a traversal from. Oh, I should note something. I presented this slightly differently. A traversal in the sense of optics is basically this, except it's a variant of this. This is what I actually have been calling a traversal, is a sequencing. A traversal is the composition of a sequencing with a map function, but categorically it's easier to think in terms of the sequencings. So if you can't get the types to match, that's why.
And I wonder if like other kinds of optics have similar theorems, like being related to polynomial functors or something.
Yeah, they definitely do. Like lenses are related to products in that way, and grades to representable functors.
Yeah, I would say, yeah. I mean, James worked on a bunch of work on this, but the general way to look at that, I think, is the profunctor characterization of optics. Right, it gives you sort of a zoo of them.
Oh, I see.
Instantiating the profunctor different ways.
Do they make that same distinction that you're talking about, though? Like, I guess I don't understand that.
What distinction?
You said there's a distinction between like traversals as optics and how you're talking about them.
No, that distinction is literally that when you said, is this the same as a traversal? I'm saying, or in an optic, I'm saying, no, actually, the type of disk that I gave you is not the same as the type of traverse. What I gave you is one of the two building blocks of traverse. You need to compose it with another functorial map to get to something that looks like traverse as an optic.
Okay.
I gave you something that's equivalent in power to traverse, but it's actually different.
I see.
Just because this is categorically easier to formulate.
Yeah, this form is easier when you're dealing with things that are functors and when you can change type in the functor type. Or in the functor argument.
Any other questions?
Very nice.
Okay.
Anyways, thank you very much. But no more talks this season. I hope to see you all in the fall.
Yeah, I will. Yeah, let me just add. I left a bunch of open weird questions at the end. If you have any ideas, and I didn't even get to all my other open weird questions, or found this interesting, let me know. I would love to have your feedback or your silly stabs at answering this or related questions or any of that. So, all right, thanks everyone.
Okay, take care, everyone. Good night, and stay cool, stay safe. Take care.